Let me forget this time.
Okay, so today we're going to look at our other comparison test. Instead of the direct comparison, we're going to look at the limit comparison test. I don't think this one comes from any strange place. I think it should make intuitive sense to you based on what we've done with limits. So it's just another way to compare one series to another. So just like last time, you have to think of a candidate series to compare yours to. So you've got two, an A sub n series and a B sub n series. So the idea is that they both have to have positive terms. We're pretty much only going to be working with those things in series unless they're alternating series, which is 9-5. So we'll see alternating series. So as long as they're not alternating, in other words, that's what this says. And also, if they're not alternating, in other words, strictly positive terms, right? Strictly positive terms in the series, which is most of the ones we've seen so far. And you take the limit of the ratio of the two that you're comparing, right? You have to figure out what you want to compare to, what B sub n you want to choose. If that limit turns out to be finite, some fixed L like 2 or 7 or 8, and that L is positive, as long as that L is finite and positive, then they do the same thing. They either both diverge or they both converge. This should make sense, right? This is just kind of like order of magnitude type reasoning that we used multiple times. We used it in 8-7. We used it all over the place to evaluate limits. If they have the same order of magnitude, then the limit of their ratio is going to be some finite number. Does that make sense? And if that's true, then they have the same order of magnitude. And if the series have the same order of magnitude, then they've got to be doing the same thing, either converging or diverging. Does that make sense to you guys? So that's the idea behind it. It's not a real complicated idea. Same idea we've been working with for other things. So let's look at these three problems, see what we can do. So this first guy is called the generalized harmonic series because it's just like 1 over n, except it's got modifications. It's kind of like a linear regression harmonic series, if you will, yeah? So it's just like a shifted and transformed harmonic series. So we call it the generalized harmonic series. If you want to name it that in your notes, great. Piece of trivia for you. So does the generalized harmonic series such that, you know, these are strictly positive. We want to work with negative stuff. Does generalized harmonic series converge or diverge? Well, what do you guys think we should compare it to? The regular harmonic series. So if we think of B sub n here as the series, I'm not going to write it like that. If I think of the series of 1 over n from 1 to infinity, that's a good comparison to take. So now what do I do? How does this tool work? It's not sophisticated. What's the machine that I'm going to use? That. So I'm going to say, okay, so if I take the limit as n approaches infinity, and usually the comparison thing you want to put on the bottom, B sub n is the thing you're comparing to. So the original thing is going to go on top. The thing we're comparing to is going to go on bottom. And you see if you can evaluate that limit. Flip. That's that, right? You can do that lots of ways. If you want to L'Hopital it, it's possible. Infinity over infinity, right? We could L'Hopital it. We could use order of magnitude. What's it go to, though? We don't even need to say.
1.
What's it equal? Equals 1 over a. And the key is a, we said, was strictly positive. So this is a finite L. So what can I conclude? So I'd say something like, therefore, by the limit comparison test, since the harmonic series diverges, so does the generalized harmonic series. Done. Shouldn't shock you that the generalized harmonic series is still like harmonic. Okay? Alright, let's look at another one. Leave that up there for a second. So what do you guys think you want to compare this to? The only real trick in comparisons is like deciding what you want to compare to, and usually it's not very hard. Every once in a while you have to be a little clever in your comparison. But what do you guys think on this one? I need a suggestion. I can't tell you right away. How about you just ignore the 1? And see what happens. If you ignore the 1, then this is the series you get, right? Let me erase the top one so get it out of our thought process here. So if you ignore the 1, you get that, right? What's that? One half. This is 1/2. 1/2 minus 2 is that, right? Or 3/2, yeah. Yeah, no, that's what you're thinking. Okay, so what's that? What kind of series is that? P-series. Is it diverge or converge? Greater than, this converges. So this is a convergent P-series since P equals 1.5 is bigger than 1. Right? So, let's take the limit. A sub n divided by B sub n. Flip action. You're going to see lots of limits like this. This is going to be the key to the ratio test, which is the last thing we're going to do before Christmas, and also the big thing for the end of series for us. It's all about the ratio test. Anyway, so flip action, and you get root n times n to the 1.5, right? All over n squared plus 1. Help me simplify, please. What do you mean, Kyle? Where? Thank you. That's n squared on top, n squared plus 1 on bottom. The answer is 1 is certainly a positive finite value. So in other words, those two series have the same order of magnitude. So in other words, they do the same thing. So since that one converged, the other one converges by the limit comparison test. I'm not going to write it out this time, just safe. That's what you're going to write. Questions? Are we okay? Yeah? Pretty easy, right? I love series. Good times. Okay, this last one, a little bit harder to decide what you want to compare to. Any ideas? It's got some weirder type stuff in it. What do we think? Remember, we're thinking about order of magnitude. See, if you master order of magnitude, so many possibilities open up in math and science. It's really a key concept in like the scientific universe.
But it doesn't matter. Can we just do like 2 to the n over n squared?
Kylie?
2 to the n over n squared.
Yeah. Kylie says compare to this. Now, of course, you might pick the wrong comparison and you might get something that's inconclusive. That's always possible, right? If you get something that's not finite L, then what you picked is inconclusive and you just have to try another comparison or try another test. Just because this is in 9.4 doesn't mean you can't still use the integral test or geometric series or the divergence test or anything else that we've learned, right? Why did Kylie pick this? I think it's a really good choice. I think it's going to work. We'll see. That was my idea too. Because the order of magnitude on top is n 2 to the n, right? The order of magnitude on the bottom is n cubed. So the order of magnitude, one of the n's cancels. Does that make sense? I think that's a good idea. Let's see if it works out. So this guy, what about this series from 1 to infinity? Is that guy going to diverge, going to converge? You think it's going to diverge? Why? 2 to the n's way bigger, so how do we say it technically? You're right, Kyle. I can't say that. That's not a series test. Go through your series test. This is what you should already be doing. You should be thinking like a flow chart in your mind. Geometric test, P-series test, integral test. We don't want to use that one unless we have to. Now you got 2 comparison tests. And telescoping, well, of course, this isn't going to be telescoping or partial fractions or anything like that. I'm leaving out one big one, the one you want. It's a divergence test. You take the limit as n approaches infinity of the sequence. What's it go to? infinity. Infinity is not 0. Remember, the divergence test says you've got to be getting small enough, fast enough, or you're not going to converge, you're never going to settle down to something. So that's going to be true, so this means that that guy diverges by the divergence test. Hey, it wasn't inconclusive for once. So if that guy diverges and we get a positive comparison here, we'll be good to go. So let's do the comparison and see if it comes out. We'll see what happens. So original divided by comparison. Flippy action. What are we going to have? Let's see. What happens with that? Those go away, right? There's no pluses or minuses in there. We can cancel it out. Anything else cancel out? I think that's it.
Combine the ends on top.
What, Gabe?
Combine the ends on top.
Combine the ends, and we get n cubed over 4n cubed plus 1. Now that limit is quite easy. It's a quarter by order of magnitude or multiple L'Hopitals. You'd have to do 3 L'Hopitals, I think. Oh my gosh, what a lot of work. Never want to do that. So the key is that this is a finite values. These sequences that we compared have the same order of magnitude. So by the limit comparison test, I'd say my sentence here would be by the limit comparison test. Since that's a finite comparison, and this guy diverges. This guy diverges. Done. Cool? You guys need me to write that out, or are we good to go? I don't want to write word cramp, you know. That's it. I think that's all you need for this section. See you next time.
Hedgehogs all the way.